Solutions to weekly contest CO9. The problem that I have chosen is longest nice subarray. So this problem is a very interesting problem, guys, and please watch the video till the very last. You're definitely gonna enjoy the solution up. This problem seems like a very complicated problem. However, it's very interesting and really simple. And even before jumping onto it, let's understand the question first. What do we need to do? We need to return the length of the longest nice subarray. And how do you define whether a subarray is nice or not? If the bitwise AND of every pair of element that exists in that subarray is 0 or not. It should be 0 for it to be nice. This is what we need to do. We need to check. And remember, we are looking out for subarrays, not subsequence. So the subarrays are always contiguous in nature. Let's walk through the same example that is specified in the equation. We have the elements as 1, 3, 8, 48 and 10. And if you carefully analyze, then this is the subarray that will give us the intended result. So the length of this subarray happens to be 3. And if you carefully check how many different pairs does there exist, 3, 8. Then we have 8, 48. Then we have 3, 48. So if you carefully see, then the bitwise AND of these 3 pairs happens to be 0, and these are the only 3 combinations that could have been generated. As a result of which, we can say that this subarray happens to be nice in nature. The length of this subarray is 3, and this becomes the answer. A few takeaways that we should extract from this question. The first takeaway is longest subarray. So remember and read this phrase twice. Whenever you see subarray, the most common approach to solve such questions is sliding window kind of a thing, and the longest keywords indicate towards using the greedy approach. So you are interested in applying the greedy approach, and since the word is subarray, what you should look out for the direction, it should be somewhere on the lines of sliding window, because the elements can't be taken in a subsequence manner. It has to be taken under the constraint of being contiguous in nature. So let's try and revise the long sliding window concepts. Let's consider a hypothetical scenario wherein let's read that the elements A and B are currently part of the sliding window, and these two elements together satisfy the constraint as per the question specified. And let's again consider a hypothetical scenario that a new element is trying to be part of the sliding window, which is C. So what do? We make C inclusive of the sliding window, and we check whether this C element can be part of that sliding window. So let's consider a happy case wherein C, when included as part of that sliding window, is a good case and it satisfies the condition appropriately. That means the length of the sliding window can be increased by 1, and the total elements in the sliding window turns out to be 3, A, B and C. All the elements are good elements as per the constraint. Let's again consider another case wherein a new element D is trying to be part of the sliding window, something like this. So again we check whether D can be part of the sliding window, and this time let's consider D can't be part of that sliding window. D is violating the entire sliding window of A, B and C treated together. So since D is violating the constraint, what we should be doing? We should be removing some elements out of the sliding window so as to consider all the possible permutations. And which element would be removed? The element that would be removed would be from the starting of the sliding window, which is A. So the new sliding window which is under observation turns out to be B, C and D. We again check whether B, C and D makes up till a happy case. If it does, then we get another happy sliding window. Otherwise, again we will be removing elements from the start. So let's consider the case B, C, D again doesn't make a happy case. We will be removing B from the starting of the sliding window, and the updated sliding window gets set to C and D, and let's assume C and D makes it a happy case. So starting from C, we will try and increase the length of the sliding window towards right. So we will again treat a new addition of the element E, and we will again go through the same process that I had talked about. So the two takeaways from this entire analysis is new elements will be added to the front, and whenever there is a violation in the sliding window, old element would be deleted from the start. This is from the sliding window concept, and now let's go back to the question and let's talk about the constraints that are specified over there. So as per the question, what we are looking for that subarray wherein each and every pair of elements and bitwise and is 0 in nature. So let's consider the case we have three elements B, C, D, and a new element is trying to be part of the sliding window, which is E. And let's consider the case that for E to be added as part of the sliding window, what should be the constraint? D and E should be 0. So the first statement is this. The second statement is C and E should be 0. The third statement is B and E should be 0. So I have taken a hypothetical example wherein I have stated these three conditions. B and D should be 0, C and E should be 0, D and E should be 0, and I have taken B as this, E as this. The value of E is same across these three equations, and C is this value, D is this value. So for E to be part of the sliding window, all these three conditions should be met, which is meeting in this case. So if you do the bitwise AND of these two elements, you'll get 0. If you do the bitwise AND of these two elements, you'll get 0. And if you do the bitwise AND of these two elements, again you will get 0. However, this would be a time consuming activity, because every time a new element is trying to be part of the sliding window, you would be iterating over the entire length of sliding window and checking whether the bitwise AND with each and every element turns out to be 0 or not, which is not a very good case to write, which is not a very good algorithm to write. In order to optimize the algorithm, what can be done? We can take one variable and let's call that variable as bit union. So that basically represents the bit union of all the elements that we have as part of the sliding window. And I have represented that element over here as B or C or D. So B or C, C or D. So this represents the bit union element for the sliding window, and whenever a new element is getting added as part of the sliding window, for it to be added there is a constraint. What is that constraint? The AND operation, the bitwise AND operation across this bit union variable that I have just created, which basically represents B or C or D, should be equal to 0. So let's go ahead and create this variable for this particular case. So what is the bit union variable for this case? It would be equal to 0, 0, 1, 1, 1. I have basically taken the bitwise OR of these three elements 1, 2 and 3. And once I have that variable with me, what do? I perform the AND operation with E, which is this one. So when AND operation is performed, the answer turns out to be 0. The time complexity for E to be added as part of the sliding window reduces to constant time instead of length of the sliding window, which is a great and significant improvement. If you have understood the past two concepts, then you have understood 80% of the algorithm. It's time to connect the dots. And let's start the iteration with the same example that was specified in the question. We have the elements as 1, 3, 8, 48 and 10. Here I have written the binary representation of all these elements. And to start with, let's create the bits union element and then initialize it to 0 for now. So all the bits in this bit union element would be set to 0. And let's write that up. So the first element that we have is this one. So the starting of the sliding window will be pointing over here, and the ending of the sliding window again would be pointing over here. So this is a happy case. The bit union variable would be updated to this element, equal to this element, because this is the only element under consideration right now. So let's update this element to 1, something like this. And let's proceed ahead. The next element that we see happens to be this one. So what do you see over here? When we perform the bitwise AND between this element and this element, what do you get? The bitwise AND leads to a non-zero value, which makes it a negative case. That simply signifies two things. The first thing is that the starting element can't be part of this sliding window, which is under consideration, because it violates the condition. Then what we should be doing in all such cases, we should be removing the starting elements. So the starting element would be removed and the starting pointer would be incremented over till here. So right now if you carefully analyze, we were trying to make 3 inclusive of the sliding window. So the element under consideration, the ending pointer was over here, and we checked that since this element can't be part of the sliding window, we updated the starting pointer. So let's update the bit union variable again, and it will be reset to 3. So this gets reset to 3, something like this. Now let's proceed ahead. The next element that we see happens to be 8. So what do? We update our ending pointer over here that points to 8, and we are trying to start a new sliding window starting from 3, and 8 is being trying to be part of the sliding window. Again we check for the same constraint, whether bit union and 8, when we perform the AND between these two variables, does it lead to a 0 value or a non-zero value? What do you see over here? You see that when we perform the bitwise AND of these two values, the answer turns out to be 0. That makes up till a happy case. Since it's a happy case, what you should be doing? It simply means that 8 can be part of the sliding window. Since 8 can be part of the sliding window, we should be updating the bit union variable, and this would be updated to the OR operation between this variable and 8 that we have, because we will be updating it to B or C in this case, to be specific. So B or C would be equal to 0 0 1 0 1 1. So this gets updated to 1. Now we have the bit union variable equals to this one 0 0 1 0 1 1, which is basically the OR of 3 and 8. Now again let's proceed ahead, and this time what we are trying to do, we are trying to increase the length of our sliding window. We are trying to make sure that 48, whether it can be part of the sliding window or not. So our E pointer gets updated over here. Again we perform the same thing. We perform the bitwise AND between these two elements. So let's perform the bitwise AND, and what do we get? We get 0. So bitwise AND is 0, that makes up till a happy case, and since it's a happy case, 48 can be made part of this sliding window. Since 48 is being made part of the sliding window, what we should be doing? We should be performing the OR operation between the previously computed bitwise union and 48. So when we perform the OR operation, what do we get? We get the updated value as 1 1 over here. So now the element under bitwise union variable is 111 0 1 1. And let's proceed ahead. The next element that we have happens to be 10, and let's extend the line over here. We are checking whether 10 can be part of the sliding window or not. So let's perform the bitwise AND between this element, the bit union element, and 10. So what do you get? If you carefully analyze, we get a non-zero value. That simply signifies that this element can't be part of the sliding window. Since 10 can't be part of the sliding window, in all those cases, what do we do as per the sliding window logic? We remove elements from the starting pointer. So what element do we have at the starting element? We have 3 over here. That means it's trying to shrink the sliding window. So the sliding window gets shrinked to something like this, and again we will check whether it makes a happy case after the shrinkage. If it doesn't make a happy case, then again we will go ahead and shrink the sliding window and we'll remove it, and so on. Rest of the sliding window concept remains the same. So once you are done with the entire iteration, once start and end meet, if they do, then we abort the process and we look for the maximum length of sliding window that exists across this entire array, and we simply return its length. We store that in a variable. So that's pretty straightforward, the regular way we operate over sliding window algorithm. In order to conclude it further, let's quickly walk through the coding section, and I'll exactly follow the same steps as I have just talked over here. Start index variable basically stores the starting index of a sliding window. Answer actually stores the answer. Bits union variable represents the bit union of each and every element that exists in my sliding window, currently under consideration. And let's look at the core algorithm, which starts from line number 9 up to line number 23. I've taken a variable I for iterating over my input array, which is basically acting as my end index, and we extract the new element that is being trying, which this is trying to be part of the sliding window. And what do we check first? Whether after the addition of this new element, whether the entire sliding window has it being gotten corrupt. If it has got corrupt, and how do we check that? First we check whether the bitwise and between the bit union variable and the new element, if it's equal to, if it's not equal to 0, then the entire sliding window has got violated. What we should be doing in those cases, we should be removing the element from the start. So which element would be removed? The starting element would be removed, and at line number 16 I have removed that element. I have incremented the start index pointer, and in case there is no such violation, as soon as we are out of this while loop that makes up till the happy case, what do? We include the new element as part of our bit union variable, and we calculate I minus start plus 1, which will give us one of the probable answer of the, which is equal to the length of the sliding window. And we take the one that has the maximum value out of the current value of ANS and I minus starting index plus 1. Once we are out of this for loop, we simply return the ANS variable. So pretty simple and straightforward, not that complicated either. However, the question looked complicated when you first read it. With this, let's wrap up today's session. I hope you thoroughly enjoyed this up. If you did, then please don't forget to like, share and subscribe to the channel. Thanks for viewing it. Have a great day ahead and stay tuned for more updates on Coding Decoded. I'll see you tomorrow with another fresh question, but till then, goodbye.